Also, power transmission, power generation SAC, Justin?
Oh, there were, it was okay. There was no multiple choice. It wasn't a calculation sack, so it was full on like explanation as well. So,
Okay.
yeah. It wasn't entirely data analysis either. So it was like kind of an concept testing kind of sack rather than using your calculator to do calcs.
What about Mithun? Have you finished your SAC for the power generation? Mithun, your SAC on power generation, have you done it or it's still?
No, our SAC on power generation isn't like anytime soon. I think it's week 2 next term.
Okay. Cool. I think your SAC is another 2 weeks time or maybe after holidays. Is that correct?
Oh no, I just did my SAC last week.
That was fields, right?
Yeah, fields.
Now I'm asking for the next one, generation, power generation.
I'm not quite sure, but it should be next term, around next term. Yeah.
Right. Guys, we'll do a quick recap on power generation and power transmission, and then we'll move on to waves. I think few people are still, SAC is due this week or maybe, this week. Lujit and Lohit, you guys finished your SAC this week, right? You finished, done? Mount Waverly, yeah. You finished your SAC this week or last week? Lohit, yeah. Okay.
You finished it last week.
Okay. Maybe I'll quick, with some few people are just still finishing off their final SAC, but I'll just quick recap about the power transmission part. I think I put it like a practice SAC for other people, just so they can do your leisure time. I think I put the answers as well. So in terms of power transmission, the key thing is how to minimize your power losses. So the power loss is mainly due to the resistance in the transmission line. So these are the two things: resistance in the transmission line and the current is the biggest culprit, because resistance is linearly related and the current is like a quadratic power loss. Like that. But the resistance is linearly related. Okay. So there was a question from one student. The question was, yes, to reduce the current, what we're doing is increasing the voltage. increase the voltage, but keeping the power constant. Being supply constant. So this is where you're using step-up transformer. I just get okay. So we'll come before we come to that question later. Now, if you get a situation where so you have a house, and then the house getting 240 volts AC, and you have like a garage or shed or something, some big far is a shed in your backyard. And then the shed has maybe globe or something, lamps there. So the lamp is operating properly, but the lamp, okay, you connect your circuit. It's about 100 meters away from the house. The resistance in the line is say 0.015 ohms per meter. That's how much the resistance in the line. But the globe has a resistance as well. Its resistance say about 12 ohms. Okay, 12 ohms. Yeah, 12 ohms, that's fine. So that's 12 ohms. So the first question is simply, so that works on 12 volts. So there you have a step down transformer here. They install a step down transformer. Stepping down. This is step down transformer near the house. So stepping down from 240 to 12 volts. Because the globe is operating, the voltage operating 12 volts. So when the globe is operating in normal condition, this is the normal condition, like voltage needs 12 volts. Normal condition. Find the power dissipated in the globe. That first part, that's quite simple. So because you know the resistance, you know the voltage, we can use our power equations. And then Ohm's law for that. So we can easily find the power, I square, V squared on R. Which is 12 squared divided by 12, so 12 watts. That's the normal operation. When it's operating normally, it should get 12 watts through the globe. But they found that the globe is dim than they expected. It's not less bright. It was found that it was less bright. Less bright than expected. The question is why? Explain. Could be 3-4 marks question. How do you explain this? Or the globe was operating at 12 watts under normal condition. It was found that globe was less bright than they expected. People who haven't done the SAC maybe answer. How do you explain that? Why the globe was less bright? Even people who've done the SAC, we can talk. Okay, sometimes they can use this power transmission question as the differentiation question. Like they use a couple of questions to differentiate the kids, right? So some years the power transmission question is one of the differentiating question. Okay, spring question, one of them, spring question, and this, and could be one of the wave question. How do you answer this? Why it is less bright? Under normal condition, you get 12 watts. Now, this is what you get. You have your step-down transformer, 240 to 12 near the house. So your resistance in the transmission line, the total resistance. How do you calculate the total resistance? I said that 0.015 ohms per meter. How do you calculate the total resistance? So I need to get 0.015 times by 100. Is that all? So that's your globe. The globe has a resistance of 12. Is that the total resistance, guys? You need to times by 2, because there are two lines. There are two lines, the input and the return line. So you need to times by 2. So that's about 3 ohms altogether. 3 ohms altogether. Yes, under normal conditions, so that's what you get. You should get 12 volts here under normal condition. But we're not getting 12 volts because you have a 3 ohm resistor there. How much current through the transmission line? Find the current through the line. The house is here. The house is supplying 240 volts AC to the step down transformer. Okay, find the current through the transmission line. Can you guys suggest me how do you find the transmission line current? Jaden, tell me. I need to call the names, otherwise you guys not answering. Oh yeah, some answers there. Just let me check. With the power, loss can be represented by square. Extremely high current would result in a significant power loss throughout the wire, thereby resulting in light globe being extremely dim when not visible. Yeah, so you find the current through the transmission line. To find that, you need to get the total resistance, R total. Now we can't assume we're getting 12 watts here. We cannot assume that we're getting 12 watts from here. So that's the catch. Yeah, we can't assume that we're getting 12 watts. So we had to assume R total. This is where you need to use your series circuit knowledge here. When you get a question like that. The 3 plus 15, sorry, 3 plus 12. Yes, true that they're supplying 12 volts from here. Therefore, current through the transmission line is 12 divided by 15. 12 divided by 15, what's that? It's like you get 0.8 amps. 0.8 amps. I'm just giving the skeleton of question, that parts of this question. It's not exactly. It's like last week's exam question, pretty much. One part, only 3% people got the full marks. Okay, one part, only 3% of people got full marks. Okay. So then you can say you expected to be 12 watts. The power, the power received at the globe then, or dissipated at the globe, you can use I squared R for just looking at the globe itself. So 0.8 squared times 12. What are you getting? I think this part, as I remember, similar part was like 4 marks. So you're getting like 7.7. The numbers are maybe not exactly, some of the numbers I'm making up. Some of the numbers may be close. So 7.7 watts. Okay, so you expected 12, it's receiving only 7.7. Okay, you can argue, that's one method of arguing. The other way of arguing, saying that you're expecting 12 volts, but since some voltage is dropping here, you can argue saying it's not receiving 12 volts. That's another way of doing it. Okay. So that's that. Now the next part of the question was what changes you can make to make this transmission line more efficient without changing any equipment. You can swap around, but you cannot change any equipment. What changes you can do to make this power line, the transmission line, more efficient? Improve the efficiency of the line without replacing the existing equipment. I mean, when you say replacing it, you can swap around, but you can't replace your transformer or wires. What's the simple answer? Make sure the length of the wire short. No, you can't, because we can't make the wire short. The reason is the shed is, you built the shed long time ago, even before you thought about setting up a light. It's well built, concreted. You know, the shed is, you've spent quite a bit of money. Can't do that. You can't change the length, you can't change the type of cable, you can't change the transformer. So you have to make use of the same equipment. Jaden, what do you think? Yeah, that's correct. Lojit, yes. Yeah, that's good. So few people coming under the 3% category. That's good. Lohit is correct. Jaden is correct. Anyone else? Vinura, Lakshray, Asta, people who done the SAC. Hassan, people who still haven't done the SAC, tell me. Shiny, any idea? How do you improve the efficiency of the transmission line? So what is the problem? What is the issue? Issue, obviously, relatively high current there. Because there will be a significant power losses. So the condition, the caveat is we can't change the power line, we can't change the transformer. Yeah, so that's the answers. I think getting few Chinese answers correct. So the solution is to move this transformer to here. So move the transformer close to that. So you transmit the power rather than transmitting at 240. You transmit the power. Sorry, transmitting at 12 volts. So you're transmitting at 240 up to here. Okay, you transmit, so you replace your transformer close to the, so move the transformer. Close to the globe. Okay, now you transmit at 240. So when you transmit at 240, so then you can see that even if you transmit at, so assuming now you can supply the exact amount of power, you can see the amount of power loss is much way less than what you get before, because here, so the current in the transmission line, let's say you transfer, 12 divided by 240. 1/20. So 0.05 or something. 5/100. That's the how much current you're transmitting through. Instead of 0.8, you're transmitting only 0.05. And then you reduce that to 12 volts. So if you look at how much voltage you're dropping here, is quite insignificant. 3 times 0.05. You might be losing like 0.15 out of 240. Out of 240, you're losing only 0.15. So therefore, you get your globe will still get the voltage at the primary side will be now 240, take away 0.15. So it's very little reduction, and then you divide by 20, you get the voltage to the globe. 240 minus 0.15. You get almost 239.85 volts up to here. And then if you divide by 20, to 39.85 divided by 20. Yeah, the globe will get how much? 11.99. It's almost 12. Who cares about 0.01? Okay, so the simple solution is to move the transformer close to the shed. Okay. All right. Do you guys think that we need to go through some transformer questions? Like I just attached that. There are a few questions. Maybe otherwise we can go. Okay. How many more you guys have the SAC to go? So I know that majority have done yet. How many people just say that we should move to waves now? Should we move to wave? Praveen, you done your SAC. Mithun, about to do. Oh, I haven't done. Shine, you haven't done. Is that okay, guys, if I move to waves? What do you think? Shiny, what do you think? The worksheets are there. Yeah, okay, just let's move. The worksheets are there. The questions are pretty good. The transformer and transmission questions are pretty good. It's a collection of all the states questions, not only the Victoria, New South Wales, Queensland, and so on. The quality of the questions are pretty good. I think, Shani, you might need to be more familiar with the equipment-wise, how they operate and things, the way that they probably going to be designed. Yeah. So look at the AC generator, DC generator, how the transformer works, and then the power line, power transmission. Sometimes they will ask you to draw transmission line kind of thing in a sec. Okay. Okay, we'll move on to waves. Right, now we know that they have not, have you guys seen the timetable? The timetables are the physics, as I remember, it was on 24th of November. Normally supposed to be about 14th. I think the 10 days shifted to towards the end. So I think 24th physics. Chem, as usual, is the day before. Chem and physics, that's not a good thing for me, but that's fine. Chem and physics go day after. That's usual practice for the last whatever years. So after English, you will have a bit of a break, and then methods, I remember, and then you have the other subjects coming up. So for waves, they have taken off some chunks. Only question is whether school going to do these sections and then include in your sec. That's only uncertainty part. Otherwise, they have taken off dispersion, polarization, Snell's law, reflection. What else they taken off? Yeah. So these chunks are taken off. I think you guys seen it for this year's study sign. Anyway, I'll just Doppler effect. They have taken out Doppler effect. Okay. But there will be more focus on diffraction, interference, general wave behavior. In terms of diffraction, interference, not only normal waves, mechanical waves, only as well as light. Okay, when you say waves, can put it in two categories. We call mechanical waves. And the other one is electromagnetic waves. All the waves need a vibration to start with, even the electromagnetic wave. If you look at the origin of electromagnetic wave, it's the vibration of electrons starting with electromagnetic waves. Now, all the waves are transferring energy. What is the difference between mechanical wave and electromagnetic wave? Yes, how do you differentiate the two types, guys? One key difference, Praveen, what's the difference? Koa, you should know. You guys done like one term of waves last year. How do you differentiate waves, mechanical waves with electromagnetic waves? Yeah, one travels speed of light. There's another difference. The mechanical waves require, remember that when Maxwell came up with the suggestion saying that light is a wave, everyone jumping in to find evidence for a medium, because they thought every wave need a medium to travel, because they knew very well about mechanical waves. So mechanical waves requires a medium to travel. Without the medium, say sound. If I take all the air molecules in this room, you might just see my mouth. It's like I put into mute. Like I can see that my mouth is moving, but you won't hear any sound. So you need a medium to travel. Requires a medium. Okay, say for example, the sound waves travel in air or solid, liquid. Water waves, like water molecules. The waves you produce in a slinky, it's the slinky itself is the medium, the metal or plastic maybe. Electromagnetic waves does not require medium. They travel at speed of light in a vacuum or in empty space. Does not require medium. It can travel through a medium, or travel through a transparent medium, or not necessarily transparent. Like if you say X-rays, it can travel through non-transparent medium. I'm talking about visible light, travel through a transparent medium. But other parts of the electromagnetic spectrum can travel through. Depends like energy and the density of the material, they can travel through medium to travel. Example, visible light, anything in the spectrum, ultraviolet, microwave, they're all under electromagnetic spectrum. Infrared, radio waves, X-rays, gamma rays, all that. All comes under electromagnetic spectrum. Okay, so that's that. And then we'll look at a bit more detail on mechanical waves. So mechanical waves can be put into two categories. We'll come to electromagnetic waves. They are behaving as transverse waves as well. That's where the polarization comes in, but they take no polarization this year. Two types, transverse waves and then longitudinal. So the transverse waves, make a big note saying that all waves, okay, transfer energy from one place to the other. Transfer energy from one place to another without net transfer of the material. There is no motion of the particle permanently. They are oscillating, going back and forth. no net transfer of matter. It's just the energy. If I speak, you hear. There are molecules in front of me oscillating back and forth. But these air molecules not physically moving from my mouth to your ear. No, then everyone gets sick, yeah, because your germs can transmit very quickly. That's not the case. Like it's just the pressure that, like we think about sound waves, just the pressure pulse moving from one location to the other, carrying that energy. Justin asking, is the light is a wave or particle? What about electron? The electron is a wave or a particle, Justin? You have both forms in both things. Light has both properties as well as particles have both properties as well. Okay. Okay. When you're defining a transverse waves where think about like a water wave, but in fact the water waves have both combination of the both, but just consider they have only the transverse motion. So that's the direction of the travel of the wave. Direction of propagation, direction of travel. That's the direction of propagation of the wave. So that's like a mean position. The particles just oscillate from their mean position, just dance up and down, while the wave is traveling from one location to the other. So in transverse waves, the particles oscillate perpendicular. Perpendicular to the direction of motion of the wave. The word propagation get used to it. Propagation is the direction of motion. Direction of motion of the wave. Okay, so can I wipe it or you guys are writing down? Okay. The particle just oscillate from their main position. So there is no physical shift. While it's moving up and down, it transfers vibration or energy to the next guy. So that vibration of energy that's carried by the next guy, he start moving. Okay. So these points will be up and down. These two going to be out of phase. This guy is coming down, the other one goes up. It all starting from, maybe I'm dropping a pebble into the water. So it all start from some sort of a vibration. Okay, so if I drop a pebble into the water, you can see the ripples forming. So ripples are sort of waves, yeah. I drop the pebble and you're forming a wave. Okay, so you need some sort of a vibration to start with. My vocal cord vibrating, I can feel that. If I touch it, I can feel my vibration of my vocal cord, that converting into sound. Yes, the vibration of a speaker finally converting into sound. And that vibration comes as a pressure pulse into your eardrum and the vibration of eardrum and then sending a signal through your, and then you hear the sound. Yeah, so it's going to be sinusoidal wave as long as it's a single vibration. Yes, you can have a multiple, like you can have superposition of few waves together that can produce. It's like when trying to create different sound using, say, your keyboard. You're trying to get the sound of a violin or trying to get a sound of a different instrument. Then you have to combine few waves together to get that. We call the superposition of the wave. Okay. The frequency of the wave is related to the frequency of the vibration. The particles will oscillate with that frequency. Okay. What does it say for the direction of motion of the wave? In transverse waves, particles oscillate perpendicular to the direction of propagation means. Yeah, just give a second. Yeah. Yeah, so on the top say direction of propagation, the bottom say direction of motion of the wave. Okay. So then longitudinal waves. Yeah, so if I take a transverse wave, just take an example like water wave. If you put a plastic bottle into a, say a wave pool, like just take a wave pool. If you put a plastic bottle, you can see the plastic bottle is bobbing up and down. It's become part of the medium plastic bottle, but the wave is not moving from one place to the other. So then the wave is sort of crashing to the other side of the wall. So you can see the particle here, the plastic bottle is moving up and down. On the other hand, longitudinal waves, where the particles, like say if I have a speaker, when you start moving back and forth, the particles oscillate back and forth. There will be a pressure variation. We'll just briefly have a look on that. And then that energy, so that's the direction of the traveling of the wave. So that's the direction of propagation of the wave. So in this case, you can see the particles oscillate parallel to the direction of propagation of the wave. Finally, someone here will hear the sound. So you're going to hear the sound. The sound will travel and reach the guy or reach the person. Okay, so longitudinal waves. The particles oscillate parallel to the direction of the motion. Motion of the wave. So the particles do not physically move from one place to the other. They just oscillate from their main position. Particles just oscillate from their main position. Okay. All right. So you can see that direction of propagation, the particles are moving. Just we'll briefly have a look. So example, the sound waves, some of the seismic waves, it's a combination. So you've got P wave, S wave, it's a combination of longitudinal and transverse wave. Some of the water waves, like in deep sea, they say rather than going be pure transverse, it's going like a circular motion. They go in circular motion means while it's going up and down, it's go laterally as well. It's going like that. So rather than going up and down, we go sideways motion as well. It's a combination of transverse and longitudinal. Sound waves, parts of seismic waves. Seismic, the earthquake waves. Okay, so just look at briefly how sound transfer energy. Sound waves transfer energy. Just take a speaker vibrating back and forth. Let's say, so you have air molecules. This is the line indicates that's as atmospheric pressure. The line indicates in the middle. This is the atmospheric pressure. That's the atmospheric pressure. So when the speaker cone move forward, suddenly what's happening, the air molecules in front of it, they're going to get compressed. The air molecule get compressed here. These sections we call a compression. Their pressure goes above the atmospheric pressure. The air molecules get compressed. Okay. Get compressed when the speaker cone move forward. So that kind of position we call it a compression, called compression. The word we're using is a compression. Letter C. Okay, so the air pressure goes above the atmospheric pressure. Pressure. Okay, next thing, it's going to go backward. So now the cone goes backward. It's kind of creating a semi-vacuum. It's not a vacuum. It's more relaxed. The particles can spread on the sideways. Some of the particles will move forward. The pressure pulse will move forward. So you have a lower pressure area here. the high pressure area now move to the right. This is the low pressure area now. The particles, some of the particles have moved away, and then particles get compressed somewhere a bit further down. Okay, so this low pressure area is called rarefaction. Rarefaction. That's a low area, low pressure area, rarefaction. And then that's we call R. Likewise, you have the high pressure, low pressure areas. So if I draw these few high pressure areas here, these are pressure pulses that already moved forward before. It's like continuously you pushing a cylinder, like if you have a piston, you push in there continuously. You can see at the end, the pressure is transferring the pressure to the end. What I'm drawing is the high pressure areas or compression areas. So these were generated by few oscillations. So now it's going moving back and forth. You get few oscillations. So on the other hand, you have these low pressure areas also in between. So you have these low pressure areas. The pressure is lower than atmospheric pressure. So these areas, what we call the compressions. C stand for compression, compression, compression. And these middle areas we call rarefactions. Rarefactions. But here they are like atmospheric pressure. The particles are a bit closer than here. Maybe I need to reduce more particles. So these are atmospheric pressure. If I draw the pressure variation, you have the highest pressure and come back to the atmospheric pressure and go below the atmospheric pressure, come back to the atmospheric pressure, go above the atmospheric pressure, come back to the atmospheric pressure, go below the atmospheric pressure, and so on. This is how the pressure is varying. That's a pressure variation. If I say this is like delta P, positive delta P, and then that's negative delta P. Delta P is the pressure variation. The midline is the atmospheric pressure. The pressure variation. That pressure pulse finally received by your eardrum or maybe a microphone or something device, and then you can amplify back, you can hear that sound back. Okay, so that's how the pressure is varying. So by doing that, the particles just oscillate from their mean position. The particles just go back and forth. They're not moving permanently. So they go for full cycle, go that to the right, come back to the center, and go to the left and come back. When they have a less pressure, they will relax, they will go, their displacement go greater. When the pressure is greater, they will come back closer, their displacement becomes smaller. Okay. Sound wave parts of, which one? Pressure part compression. This part was parallel to the sound waves. Parts of seismic, like earthquake. Some parts of, because there are P and S, some parts of. earthquakes. Earthquakes, quarks, I don't know how to spell. So that's some parts of the earthquakes. So they are the seismic waves are all longitudinal waves. So the key one is a sound wave. Now, both longitudinal waves and transverse waves can be represented by displacement distance graph or displacement time graphs. Both transverse waves can be represented by displacement. The displacement here refers to the particle. The distance refers to the distance traveled by the wave. Displacement time graph. Okay, displacement distance and displacement time graphs. So we'll have a look these graphs separately, and then we'll just develop the wave equation. Okay, so displacement distance graph. Here the displacement refers to displacement of the particle from its mean position. Distance refers to how far the wave has traveled. How far wave has traveled. All right. So if I start plotting this, could be in meters. Sorry, that's displacement. So we have to give the direction. That's why we get positive and negative, like a sine graph, and then the distance. So these are we call traveling waves. If you generate the wave at one place, it travels until its energy dissipates completely. Okay, other type of waves we're talking about is the standing waves or stationary waves. It's a displacement distance graph. Okay. So draw a couple of cycles. Okay. So the displacement is how far, as I said, from mean position. That's from the center. This is what we call the amplitude. Hey guys, now when you're listening to a radio, if you can't hear clearly, what do? Yes, too faint. The sound is too faint. What do? Immediately you increase the volume, obviously. When you increase the volume, what part of the wave you changing? Are you changing the frequency? Are you changing the wavelength? Are you changing the speed? What are you actually changing by increasing volume? You're obviously increasing the energy of the wave. That's why you can hear more. What part of the wave? Yeah, it is the amplitude you change it. So when you're increasing your volume, you change the amplitude. So I'm just trying to say the energy of the wave related to amplitude squared. Why squared? We don't talk about negative volume, right? We try to make it everything positive. Whenever you're trying to consider that negativity, remember the RMS definition? We're trying to make it everything positive. You square it, amplitude squared. So the energy of the wave depends on proportional to the amplitude squared. It's like whenever you're talking about the brightness of the light. Yes, we don't have a negative brightness. Yes, it's always positive. Even the voltage is going the negative way, the brightness is always positive. So the energy of the wave proportional to amplitude squared. Basically change the amplitude by changing the volume. Okay. Now, the distance traveled during the one cycle of motion. So say the particle is moving either up and down that way, coming back to the center, going below the that position, coming back. That's called one cycle. Or if we consider the longitudinal wave, going to the right, come back to the center, going to the left, come back to the mean position, that's one cycle. So we're defining, so this is a quarter of a cycle, half a cycle, 3/4, one full cycle. The distance traveled by the wave during one cycle motion of the particle is what we call the wavelength. The symbol is lambda. We measure in meters. Okay, wavelength. Wavelength is the distance traveled by the wave. Don't mix up with the period yet. This is your x-axis is distance. One full cycle of motion of the wave. So wavelength, amplitude is all clear. You can see it's 2 cycles there. And then we'll talk about displacement time graph. Displacement time graph. Again, the displacement refers to the displacement of the particle from its mean position. Time refers to time to complete, or how far the wave has traveled. or the time taken for the wave to travel. Time taken by the wave to travel. Maybe I'll just find more space somewhere. So the time refers to time taken by the wave for the propagation. Propagate from one position to another. So when you say wave traveling, we talk about the energy to another. The good example, someone said that the very good example to indicate that there is no net transfer of the particle, but the wave is carrying energy, is a Mexican wave. You can see people are moving up and down. Yes, in a cricket ground or whatever. Yes. Praveen and Justin sharing the same joke. We like to hear that as well. So, okay, so Mexican wave, so people are moving up and down, but they not physically move into another place. You can see the wave is sort of moving around the whole stadium. Okay, so they carry that energy around one position to another. So this is a displacement again. That's in meters, that's in seconds. Then time to complete one cycle is called period. So that's what we call one period. The lambda could be any. So these are waves. Say, if I draw a wave, so crest and trough. So basically, if I take a simple transverse wave, these are wave crests and troughs. And the distance between two adjacent wave crests is one wavelength, or even adjacent two troughs, that's wavelength. So that's what we call one period. So the time to complete one cycle or period, capital T, called the period, capital T, okay? Time to complete one cycle is called period. These are just general stuff. Look at the wave equation, V equals F lambda, how to get that. You guys done these stuff on year 9, I guess, yeah? Year 9, 10, year 8 is part of stuff. Yeah, just to need to cover that. Can I get rid of this? Yes. Okay. Now construct the wave equation. The wave equation will give you the connection between the frequency links, the speed of the wave, frequency frequency is number of cycles per second. Wavelength and the period indirectly. Okay, so there's a crest, troughs, distance between two crests or two adjacent troughs, that's one wavelength. All right. Now just define what the frequency is. Frequency is number of cycles per second. The period is time to complete one cycle. The frequency is number of cycles per second. So unit can be per second or hertz. 1/second, or we call hertz. After Henry Hertz. Okay, speed of the wave, distance over time. So the wave, when the wave travels a distance of wavelength, one wavelength, it takes one period to complete one wavelength. You can use that equation on the side as well, lambda over t. But we know the connection between the frequency and the period because your frequency is number of cycles per second. The period is number of time for one complete cycle. The connection is that. F equals 1 on t. Therefore, you can write the equation. So you can replace 1 on t with F. You get V equals F lambda. That's what we call the wave equation. Whenever we try to deal with electromagnetic waves, we're replacing V with C, letter C. Okay. These are just self-explanatory so far. Training guys are ready. You can just start wiping things. Hey guys, I don't know because they have started more restrictions again. Yeah, they imposed on the restriction today or last night with the increasing in number of cases. So I'm not sure what Madhir is doing. So he's doing partly. I just asked him, but he didn't give me a clear word just to I can open and do the classes or not. So. What do you mean by step down by one level? I don't understand. Yeah, okay, so whenever he sees that, okay, I can do the classes, I'll do it. But if there is a directive coming from the state government or something, then we have to abide by that. So you can't just go against it. If something goes wrong, you'll all be in trouble. Okay. Yeah, you can still pick out the booklets if you this week for your players. Yeah. Yeah. So people who want to come and pick up the booklets, you can pick up the booklets, guys. I can keep the booklets at the front of the doorstep. I think some managed to pick it up because I managed to print the power generation booklet with the field booklets. So it's no necessary to come. So that's the same one. Okay. Yeah, because I just leave it outside. That's fine. Okay, guys. Okay. Get a simple example. For speed of light for electromagnetic waves, waves, the V is replaced by C. So the equation becomes C equals F lambda. Right, what's your favorite radio station? Can you find the wavelength of your favorite radio station? Find the wavelength of any FM radio station. It's megahertz. Find the frequency of the radio station in kilohertz if lambda is equal to 400 meters. Okay, give it a try. Find the wavelength of your, I don't know, is it Nova or something, 100.3 radio station. Anyone have some guide, idea what's the size of the wavelength of a FM radio station should be? In sometimes like this loose term saying it's the size of something. Anyone know about it? Size of, what's the size of AM radio stations and FM radio stations? Sometimes comes handy in a question if they ask you. Okay. So C equals F lambda. Megahertz means million. Your lambda equals C on F. C is the speed of light, which is 3 times 10 to the power 8 divided by the frequency is 100.3 times 10 to the power 6. What do you get? Three times 10 to the power 8 divided by 100.3 10 to the power 6. Size of a van or size of a car. Normally called size of a car. Wavelength is size of a car. Step down. Is it in hundreds for AM radio? What do you mean by hundreds? So yeah, I was asking to give in kilohertz. Yeah? It's 400. Wavelength was 400. I was asking to give the value in kilohertz. The sound waves can travel fast in solids because the particles are closer, because the pressure pulse will be transferring very efficiently. That's why, like, if you are the speed of light, Mithun, that's the speed of light. C is the speed of light. Hey, you guys remember this from special relativity? Speed of light. Okay. Now that's why, like, if you're in a rural town, if the train is coming only every one train per day or something, if you can't hear the sound of the train, like if you are waiting, if you can't hear the sound, what you can do, you can keep your ear on the track. Yeah, that's what people are doing in rural places. because the how far can a radio wave travel depends on, because the AM can travel quite a bit of distance. FM can interrupt with the mountains, trees, some dips. That's why FM radio stations can't travel that far. They can interrupt. But AM can travel far distances because they are longer wavelength. Because we learn here about diffraction, the diffraction has a significant effect on the wavelength. Longer the wavelength, greater the diffraction. So they can bend around all the obstacles. But FM can't bend around as much. Okay. And also again, it depends on the energy they transmit through. Can FM travel underground? Probably not, because that's why you need to put like repeater stations. When they opening up the tunnel in Monash Freeway, there was no FM reception at the beginning. They had to, if you had to install some sort of a repeater stations inside to get the transmission going. No mobile signal, no FM, AM radio. Even the AM couldn't get it inside, as I remember, at the very beginning. So they had to install some sort of a booster stations, booster antennas or some sort of thing inside the tunnel. Yeah. Because now you can get the radio signals. Because they had to install some sort of devices there to get that signal back. Okay, if you look at the second one, frequency of the radio station, kilohertz. So the frequency is C on lambda. So that's 3 times 10 to the power 8. The lambda was 400 meters. That's in hertz. So 3 times 10 to the power 8 divided by 400. Yeah. So 7.5 times 1, 2, 3, 10 to the power 5. 10 to the power 5 hertz. So if I divide by 1000, I get like 750. Not that close to, because 774, you can see the ABC radio. So your wavelength would be slightly different to this. So what you have to remember, the wavelength of an AM radio station it's like the size of a football field. Then wavelength of an AM station or FM station, these just a ballpark, just numbers to remember. FM station, size of a vehicle, size of a car. Size of a football field, size of a car. If you get something wrong, go wrong, you can just, it can't be, that can't be right. All right. Seconds. displacement. So that's in centimeters. That's in milliseconds. Find the period of the wave. Frequency of the wave. If lambda equals 3 meters, find the speed of the wave. Simple questions. Period, frequency, and the speed. Work through quickly. Slight glare. There is a slight glare on the white. Oh, okay, there, yeah, okay. So the numbers are, this is like 40 there. If you can't see, that's 40. Maybe I'll just remove that, the glare part. That's 40. That's the displacement. Am I avoiding? Yeah, I'm just slightly avoiding that. I'll get rid of that. Oh, I think I can get rid of that. Okay. Period of the wave, frequency. My number seems not matching here. Maybe that's not there. Let's check. Yeah, I think the 20 should be here. Yeah, okay. 20 should be there. Sorry, yeah, my numbers are wrong there. Look at how many cycles are there. So if you look at it, after 20 milliseconds, there's one cycle. It's a quarter, half, 3/4, one cycle, and 1 1/4. So that's 1 1/4 periods. You can say part 1, 1.25 t equals 20 milliseconds, -3. Or you can give the period in milliseconds, that's fine. That's in milliseconds. And the period going to be 20 divided by 1.25. So 16 milliseconds. One cycle is 16 milliseconds. So therefore frequency, F equals 1 on t. Convert milliseconds into seconds. So -3. You get 62.5 hertz. The last part, number 3, we're looking for V equals F lambda. F equals 62.5, lambda equals 3. 7.5 meters per second. Okay, that's simple one. Hey guys, consider this traveling wave. Consider a traveling wave traveling from, say, towards right. Traveling transverse wave. Moving to the right. Okay, so it's moving to the right. I'm just drawing that now. This is the mean position of that wave. The particles are different locations. There are particles, they're moving, just moving up and down. Particle A, particle B. Okay, maybe put C there. Particle D. Which direction these particles are moving at the instant? Remember the wave, the particles are continuously moving up and down. So ask you what direction they're moving, up, down, or they stay stationary? Kind of. If you assume 3/4 of the period, 10 milliseconds, then the period is, did I made a mistake? That's 3/4 is 10. Yeah, again, yes, that's true. The 20 milliseconds comes here. Half, 3/4, half, 3/4, that's 20 milliseconds comes here. So 1 point, yeah, I think I stuffed up. That's 1.5. Sorry guys, I think I made a mistake there. 1.5, 1.5. Because if I put 10 here, that's about 3/4 of the period. Half, 3/4, and quarter another half. So that's 20 should be coming here. So that's 1.5 is 20 milliseconds. Sorry, 1.5 period is 20 milliseconds. So that's 1.5. So I was putting 10 milliseconds every 3/4. So if you 1.5, it should be 20 there. Thanks, Lohit. So 13.33. Milliseconds. -3. $75 hertz. $225 meters per second. Yeah, that's about 225. So sorry about that. Yeah, so the period is in milliseconds, Naveen, yeah. That's where the difference. So these periods are beside milliseconds, not second. MS means millisecond. Okay, guys, now find the direction of the motion of these particles at the above instant. So the simple method is to find just draw like a small phase shift. Now these points are obvious, like this at the topmost point, they definitely should come down. This guy definitely should go up. So sometimes it's a bit uncertain to talk about these ones. Small translation, like this translation has to be less than a quarter period. Small phase shift to the right. Small translation of the wave to the right. Less than quarter period, don't draw too much. So my peak should come somewhere here. If I draw that, then you can easily see what direction the particles are moving. If the peak shifted to the right now. Okay, you can see that shifted. The particles are moving up and down. That should be going down. That is going up. That is going up. That is going up. You can see A has gone up or A has gone down. But B, C, and D up. You give us more translation to the right and figure it out, what direction they are moving. A is not stationary, they just, I mean, at that instant stationary, but about to move down. It's about to move down, and the lowest one's about to move up. Okay, so give another example. Again, another traveling wave. Now these waves are traveling to the left. That wave is traveling to the left. So identify the direction of motion of the following particles. A, B, C, maybe D. So identify the direction of motion of these particles, A, B, C, D. The wave is traveling to the left. It has frequency related to the frequency of the vibration. Say, for example, your speaker is vibrating at 600 hertz. Your particles are oscillating at 600 hertz. But they're not physically moving from one place to the other. Can you guys put your answers for the second scenario? What direction they're moving? Up, down, left, right? It's a transverse wave. to gain a transfer. Okay. Yep. Yes, good. Yeah, go ahead. A, yep, that's correct. What about B? Good. It's traveling to the left, Nevin, not to the right. Yeah, that's correct, Asta. Yeah. So if you give a small shift, this the peak must have shifted so that you can see it's going up. Just going up. Just down, that's down. AB is up. Up. Down. Down. Okay. Now look at the superposition of two waves. It's the vector sum of the two waves in amplitude. Before we do that, just quick question, another question. This is the ship conducting some sonar measurement to find the depth of the seabed. Okay, so it's conducting sonar, so they have a detectors, they send in the signal, they have the detector. So they're trying to measure the depth of the sea. So they have to use high frequency sound, because if we send low frequency sound, hey guys, what's the human hearing range of the frequencies? What is the human hearing range? Yes, what's the human hearing range? Anyone know what's the range? When you get older, you're losing, yeah, that's correct, Lohit, yes, that's correct. 20 to 20,000, you get, when you get older, you're losing pretty much the high frequency end, and then you're losing some low frequency end as well. That's why when the kids are playing your ringtones with a high frequency ringtones, the teachers can't hear. The kids can hear, but the teachers can't. Because when you get older, you're losing your high frequency end. And the dogs can hear high frequency sound. That's why dogs' whistles are normally made from like high frequency sound. So although we can't hear, the dogs can hear. Some animals can hear low frequency. So when you're using the sonar measurements, you need to use very high frequency. It's like even ultrasound, they're using high frequency. So let's say the frequency of the sound is say 3 kilohertz. The speed of the sound, let's say 500 in water. So the detector receives a signal. every 2.75 seconds. First question, find the wavelength. The second one, find D. Find the depth. Seabed. Find the lambda. What do you get for the lambda? Because of lambda. This V is 500. 3000. It's about 0.17. So what do you need? Like in a radio waves, you want to spread, but in a sonic measure, you want to go over them straight and hit the target and come back. Okay, that's the wavelength. What about the depth? Yeah. What about the depth? Anyone manage to get in meters? What is the value of D? No answer? Come on. Should have got the answer a long time ago. Hmm. 4,000. Is it? Can't be. And decimal places are wrong. So the detector receives signal in every 2.75 seconds. Remember, it has to send the signal and then reflect back. So that means 2D, the time 2.75, you send the signal and it's receiving. Okay, so that means that twice the distance takes 2.75 seconds. The time to one way because 2.75 seconds is sending the signal to the sonar and it hit the seabed and reflect back. And he send the signals, receive the signal every 2.75 seconds. Time to one way travel should be half that. Something like that, yeah. And the depth is speed times time. Yeah, I think 600. Some people getting the right answer. 687. Yeah. Hassan getting Jaden. So 2.75 divided by 2 times by 500. 687.5. Okay. So we'll talk about the superposition of the two waves. Okay. Principle of superposition of two waves. Okay. When the two waves traveling, say for an example, they're traveling in opposite direction. Okay. When they're traveling in opposite direction, when they meet each other, they're going to combine the amplitudes. They're going to combine the amplitude, simple vector sum, combine the amplitudes, but they will continuously travel. Say for an example, if I draw wave pulse coming through and there's another wave pulse. If they're traveling in opposite direction, so this wave will travel with a certain speed, and that continuously travel forward. This guy is also traveling. So at one point they're going to meet up each other. So there will be a point they're going to meet each other. So the forward, the wave moving to the right will be that way. The wave moving to the left will be that way. If the amplitudes are same, the final outcome will be nothing. They cancel each other. But they will continuously travel. There is no harm to each other. They will continuously travel. This guy will travel forward. You will have that combined effect in between. But then finally they will separate. There is no effect to each other. No effect to each other. They will travel, continuously travel without interrupting their amplitudes. So they will both travel. That's basically the principle of superposition. When the two waves traveling in opposite direction, when they meet each other, the amplitude will be add up as per the vector sum. And two waves traveling in opposite direction. The amplitude vector addition or subtraction, okay, vector addition during they interact each other. During the interaction. However, they will leave permanent effect onto their amplitudes. When they separate the interaction. There is no change in energy or anything. During the time when they combine, yes, they will combine, they have the combine effect, but soon after they separate each other, they will go as usual. The point of contact, so what will happen? You will have that, and then you will have that. As a result, you will get a greater amplitude at that point when they meet each other. That's the vector addition. So if one is say 5 or x or something, if the other one is x, it will be 2x. That amplitude will be 2x. Simple addition. The same thing apply, like if they can cancel each other as well. So one is coming that way. The other one is coming opposite way. When they meet each other, your resultant value would be 0. That's your resultant. This is the resultant. That's the resultant. But they will separate again. Okay. That will be that. If I ask you to plot the outcome of two waves, say one is coming like that, the other wave is coming like that. Is traveling that way, but they're traveling in the opposite direction. When they come closer, yes, but if they ask you, exactly, you get a simple question like that, ask you to draw the resultant effect. That's that. Wave pattern. Show the resultant wave pattern. So what will happen, the resultant wave pattern, maybe they will cancel each other. We have that, nothing, and then you have that. That would be resultant at that instant. The top one will be cancel each other. These two parts will cancel. Okay. Now you guys have some homework to do, so we can just spend maybe 5 minutes to go through some questions. We have this worksheet, guys. Have a look at wave 0, 1, or whatever they call. You can spend 5 minutes. Okay, just get that wave worksheet and go through some questions starting from page 1. Maybe you can finish 2 pages very quickly. Very simple question. Okay, it's called something topic test or whatever they call this one. Wave booklet. It's not a booklet, it's just a few questions. So we go through a few questions very quickly, guys. You got 5 minutes. 5 minutes long, more than enough to do the question. Ravi, can you find that paper? Yeah, worksheet, papers. Okay, go through some questions quickly. Mithun, tell me the answers. So you have the wave and they give a value of X and Y, identify these places. What's the value of X? What's the value of Y? Next question, they ask you to find the frequency. They ask you to find the period, ask you to find the speed. And the best description of the motion. What direction the particle A, which direction the particle A moves. Okay, you can just smash it in 2 seconds. So we'll go through harmonics and maybe the diffraction and interference stuff next week. So the school's holiday starting, so we can finish it off. We can finish it off during the holidays, no problem. And then we can start the last section. They haven't gone through, like they got rid of Snell's law, which is one of the easiest questions in the exam. And then mostly diffraction, polarization, Doppler effect, they were all qualitative type question, like either multiple choice questions or explaining questions. They all taken off. Total internal reflection, they're taken off. But you have to let me know if the teacher's doing that, we need to go through it. Because that probably will be in your set. Principle of superposition of 2 waves. I think I've written as 2 waves. It should be 2 waves, okay? It could be more than 2 waves as well. You can superposition more than 2 waves too. So you answer to question 1. That's X. So the amplitude, they say amplitude is 0.2, then this is 0.2, X should be 0.4 then. 0.4 meters. The distance Y is 1.25 period, wavelength, 1.25 lambda equals Y. So they give the wavelength, so the 1.25 times 2.4 is equal to Y, about 3 meters. So your A is, your Y is somewhere here, Y. That's 1 wavelength and a quarter. Part C. They saying that these waves passes a fixed point. 3 of these waves passes in 12 seconds. So the frequency we're looking for every 1 second. So to get how many waves passing through every 1 second, 12 waves in 12 seconds, or 3 waves in 12 seconds. We're trying to find per second. It's going to be 0.25. The period is easy. 1 on F, 4 hertz. Yeah, 4 seconds. Part E, what's the speed? You should get like 0.6 meters per second. The frequency is that. Wavelength is 2.4. And if we draw a translational graph for F, you should get B downwards. Okay, maybe I'll let you guys go. Okay, you guys finished off rest of the questions, yeah? So I'm not going to, some of them are interference, diffraction. There is a Doppler effect question as well. Doppler effect. If the teachers go through Doppler effect, then you have to do it. Otherwise, you can finish it off this section relatively quickly. Okay, maybe I'll let you guys go. Any question, guys? Anything? Last minute questions? Anyone need any materials or maybe need to modify materials to match your sacks or anything? All good? Okay. Then I'll let you guys go. Okay, I'll see you next week. Okay, it's again going to be online, unfortunately, until I get the clearance from state government and Madeira as well. Okay, I'll let you guys go.
Thanks, sir.
Goodbye. Goodbye.
Yes, sir.
Thank you, sir.
Thank you, sir.